Hi, hello everyone. My name is Attila Böröc. In cooperation with the Erasmus Plus program and the Hungarian Octopus Youth Association, I would like to invite you to our solar energy course. Me and my colleagues will guide you through the information you need to know about the sun and the solar energy. After watching the 15 video chapters, actually at the end of the course, you will understand our star and the energy it radiates. If you wish, at the end of the course, you will be able to produce electricity, heat, applying the energy of the sun, and even you can build your own sun cooker. Let's run through quickly on the topics we will be exploring in this course. First of all, we need to understand the operation of the sun. On the second video, we will learn about the sunshine traveling through the deep space, our atmosphere, and the part of it arriving on the surface of the Earth. We know also that life without sunshine is almost impossible. We will check this statement in agricultural terms. After this, we will talk about the history of the solar energy, and we will make also an international lookout. Then we will check the possibilities to transform the sunlight into heat, electricity, and biomass. One of my colleagues will explain you the different solar cell types. As everything has two sides, the usage of solar energy has advantages and some disadvantages as well. We will evaluate both sides. The last chapters will show you how to use the solar energy in modern agriculture and how can you build your own solar set. So let's begin with the first topic. In the next couple of minutes, I try to explain you how is the sun producing the huge amount of energy, what layers it consists of. We will make some guesses about its age, and I will also tell you some enormous numbers, actually some details about it. So what do you see on this picture? This is the endless universe. This big disc-like thing in the middle, this one, is the so-called Milky Way. On a moonless clear night, you can observe it with the naked eye. In the middle of the thing, you can see the black hole. You don't? Me neither. Due to their huge gravitational force, it is surrounded with big, bright stars. The whole mass is rotating around it with the speed of 220 kilometers per second. We are on the inner edge of the galaxy's Orion arm. There, around 25,000 light years from the central black hole. It is far away, actually. 1 light year is 9.5 trillion kilometers. The white dots everywhere are the stars, like our sun, actually. You see there are some of it. According to Wikipedia, there are around 100 to 400 billion stars in the Milky Way galaxy. Each star has its own solar system, which consists of planets and lots smaller objects. Because of the sun gravitational force, these objects are rotating around it. Just like in the galaxy, the stars are rotating around the black hole. As you see here, not too far from the sun, in the third position, is our Earth. This is actually our good luck. In case we would be a bit closer or a bit farther, the temperature wouldn't be good enough for us. As you see, there are 8 or actually 9 planets in the solar system: the Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and the dwarf planet, the Pluto. As you can see, there are some size differences among the planets, but all are a dwarf comparing to our Sun. You see also the rotation plane of the planets. Some are vertical, but some are with horizontal rotational planes as well. So what is the Sun? The Sun is the largest object in the solar system that provides heat and light for us. As we discussed before, it is essential for almost all life on Earth. Just almost, because there are some living forms, they don't need energy from the Sun. For example, deep sea bacteria. Its gravity and the rotation keeps all of the planets lined up in their orbits. Without the gravitation force, the planet would fly away, but without the rotation, everything would dive into the Sun. Based on its spectral class, it is a G-type main sequence star, which means it is in her mid-age. It is referred as a yellow dwarf, but this is not completely accurate because the light is closer to white than yellow. As I mentioned before, it is huge. It contains almost all the total mass of the solar system. The rest, the planets, moons, debris, altogether are less than 0.2%. At around almost 1.4 million kilometers wide, the Sun diameter is about 110 times wider than Earth's. Because its core has a big pulling force and rotation, and because it has no solid surface, its shape is perfect sphere. Its rotation period is really interesting. The Sun rotates faster at its equator than at its poles. The differential rotation is caused by a convective motion due to the heat transport and the Coriolis force due to the Sun rotation. In a frame of reference defined by the stars, the rotational period is approximately 25.6 days at the equator and 33.5 days at its poles. Due to the deviation, strong magnetic disturbances occur, leading to the formation of solar flares and sunposts, especially during the 11-year replacement of the magnetic poles. Its volume is more than 1 million times, and its mass is more than 100,000 times of the Earth. The gravity on equator surface is 28 times of the Earth. Just imagine it is 28 G. A fighter pilot can tolerate 9 G for a time in a special government. This with numbers, if you are normally 100 kilogram, 28 G means for you that you feel 2,800 kilograms. Its temperature is also incredible. Of course, nobody could go close to measure it, but scientists determined that in the center, the temperature is around 15 million Kelvin. On the surface, it's only 5,000 to 6,000 kelvins, and in the corona, around 5 million Kelvin. I could say easily Celsius as well, because with these big numbers, it makes no big difference. The difference is only 270 degrees. 0 Celsius is actually 273 Kelvin. Its color hides an interesting paradox. With the public consciousness is that the Sun is yellow, the light coming from it is actually white, even a standard of white. So why yellow then? There is several explanations for this phenomenon. We see the cloudless sky blue. It is because of the refraction of the atmosphere. The higher we are, for example, in an aircraft we're climbing up, the less air particles make less reflection, so the blue is getting darker and darker. So the reflection changes the color of the Sun. And there is an optical illusion as well, which we see because of the contrast of the blue sky. I'm also sure that everyone loves the sunrise and the sunset, I mean mostly the sunset because sunrise is too early, especially for me, we can only look more or less into the sun when it is lower on the sky. In this case, the light is discolored from yellow through orange to sunset red due to the dust floating in the atmosphere. And also there is a tradition, an ancient tradition, to regard the sun as yellow, as our ancestors identified it with the fire, which flame is yellow actually. As I mentioned before, the surface temperature of the sun is 6,000 degrees. Any surface at that temperature will generate heat and light. The burners of an electric stove or a toaster, as you see on the picture, are just a few hundred Celsius, but when they are turned on, they emit heat and light, red hot light. If we could raise the temperature to 6,000 degrees, they would become white hot and emit light very much like the sun's. On this slide, you can see the composition of the sun. Because of the excess heat in the sun, the elements are not in the same form than in the Earth. Here on the Earth, the elements have protons and electrons as well. In the sun, one or more electrons are detached from the atoms. This is the so-called plasma state, where the substance is a mixture of plasma ions and free electrons. The two main elements in the sun are the hydrogen and the helium. As you see the diagram here, the numbers differ from the chart. Here you can find 73% hydrogen, but here is only 70 by mass. But all the sources you can find are a bit different in the numbers. The explanation is quite easy. The sun converts hydrogen to helium in its core, so the ratio of the two elements is continuously changing. It will be more and more helium and less hydrogen as we progress through time. Apart from the two main elements, everything else, iron, nitrogen, calcium, and so on, are less than 2%. Okay, we just finished the first part of this chapter. There are some questions you should be able to correctly answer in case you paid proper attention in the previous minutes. First of all, where are we in the endless universe? The correct answer is somewhere in the inner edge of the Orion Arm in the Milky Way galaxy. Second question, what is the shape of the sun? Do you remember? Because its core has a big pulling force and high rotation, and because it has no solid surface, its shape is perfect sphere. Then, what is the surface temperature of the sun? We remember it is quite hot. In the core, around 15 million degrees, but on the surface, they are much colder, around 5,000 to 6,000 Kelvin. And the last question, what are the most common elements in the sun? The answer is easy, hydrogen and helium, approximately 70% and 28% by mass, but it's changing. All the rest are less than 2%. Now, in this part of the video, we will discuss about the operation of the sun. The sun is producing a big amount of heat and light, but the question is how? I mentioned just a few minutes before that it converts hydrogen into helium. This occurs because the sun is very hot. And the sun is very hot because of the fusion releases a great amount of heat. That's why the fusion is called chain reaction. In other terms, it is a nuclear reaction inside in the core. As you see on the slide, in a typical nuclear reaction, several subatomic particles come together, interact, and several possibly different particles emerge. You can see the chemical equation On the left side, on the input side, 4 protons and 4 electrons, basically 4 hydrogen atoms. And on the right side, the output here, it's 4 protons and only 2 electrons. It means we lost 2 electrons on the right side. According to the law of physics, the mass became energy. It has 2 forms, motion energy and also gamma rays. As Albert Einstein found, a very small amount of mass can convert it to a very large amount of energy. In fact, 1 ounce of matter converted to energy by fusion could supply all the energy your home and your car would need in a whole year, plus 5,000 other people's homes and cars as well. In the sun, not an ounce, but 508 million tons of hydrogen are converted into 504 million tons of helium every second. The remaining 4 million tons of matter are converted to energy. So it is incredibly hot. The different properties of plasma, such as temperature and density, create various layers within the sun structure. We will check now the structure of the sun from inside out are there. First of all, inside the core, then the radiative zone, then the convective zone, then the photosphere, the chromosphere, and also the corona. First of all, we will talk about the innermost part of the sun, the core. The innermost 20–25% of the sun radius is actually the core, where the energy is created. Due to the immense nuclear fusion we discussed before, the temperature it's really hot here. It's around 15 million degrees. Above the core, there is a thick and dense radiation zone. The energy coming from the core is traveling through this layer as photons. One of the interesting features of the radiation zone is that it holds up the protons. The photons go through a series of collisions in this layer, and because of this, it takes 1 million years for a photon to get through to the next layer. The temperature here is a bit cooler than in the core, about 10 million Kelvin. Next layer is the convection zone. Convection is a process in which warmer and less dense matter rises and cooler, more dense matter sinks. Exactly the same than in our atmosphere, how the weather fronts works. This layer is actually between the 70% of the sun radius and the point close to the visible surface. And the temperature is dropping further down to 5 million Kelvin in this layer. The next layer is the photosphere. This is actually the visible surface on the sun and the first layer in the sun atmosphere, which is the tiniest, only a few hundred kilometers thick. The energy produced in our star is radiated in this layer in a form of light. Here we can observe the sunspots as well. A couple of slides later we will discuss about them. The temperature here dramatically drops to 6,000 Kelvin. The next layer is the chromosphere. It is actually the middle layer of the sun atmosphere. As you see, the temperature here increases again. It reached about 10,000 Kelvin, and this layer radiates mostly the sun harmful ultraviolet waves. The corona is the outermost layer of the sun atmosphere. It extends millions of kilometers above the sun visible surface. It consists of low density gas, and because of this, the temperature is really high, 1 million degrees. Actually, we can observe it when there is a solar eclipse or with special telescopes. After finishing the exploration of the sun layers, we will discuss now about some interesting phenomena as sunspots, solar flares, and coronal mass ejection. Sunspots. The sunspots are temporarily dark, relatively cool blotches on the sun-bright photosphere. They can occur mostly in past due to the strong magnetic concentration, which inhibits the convection we were talking a few minutes before. They can be quite big, and we can observe them mostly at sunrise and at sunset. They are relatively cold comparing to the surrounding photosphere. Solar flares seem to be energized also by strong local magnetic fields. They are sudden, tenuous, explosive outbursts of light and invisible radiation and some material from the sun. These short-lived explosions last mostly just a couple of minutes, but they can release a huge amount of energy. The third one is the coronal mass ejection. They blast plasma out from the corona, and this rises tens of thousands of kilometers up into the deep space. The phenomena you can feel also because they release a huge amount of energy, which is affecting the modern technology. Once, disruption in power transmission, and second, disruption in radio communication as well. This part of the video is over, so with a short quiz, we will check your knowledge then. The first question is, what are the layers of the sun? From inside to outside, check them. The number one is the core. Number two is the radiative zone. When we are coming more out, the third one will be the convective zone. Four, the photosphere, where the sunspots are. Five will be the chromosphere, and the six is the corona. The second question, in which layer the nuclear reaction takes place? It's quite easy. We mentioned many times before that it is in the core. And the last question, which layer is cooler, the photosphere or the chromosphere? It is the photosphere, of course. The last chapter in this video is about the age of the sun. Our sun is a second or third generation star. This means the solar system was formed from the interstellar gases of the universe and the remnants of its former stars, which were destroyed as a supernova. It happened approximately 5 million years ago. This is evidenced by a presence of heavy elements, iron, gold, uranium, and so on, as these substances are typically formed during supernova explosions or in first-generation stars. In the present, in her active stage, it is producing energy, but after running out of fuel, it will stop producing energy, but this will be approximately 5 million years from now. This will be her passive stage. First, we will check the active stage. The life of the sun began as a protozone forming in an extensive molecular cloud. In the Milky Way, a number of huge molecular clouds have occurred and still have today. They are called stellars. Due to a greater external influence, such as supernova explosions, inhomogeneities and nodules formed in the relatively dense material in the clouds. Due to the gravitational concentration, the material condensed and more heat was released, heating the material in an extreme way. In a few million years, at its center of this protostar, the temperature reached a few million degrees and the hydrogen fusion had begun in it. And so the fusion lasts as long as there are enough hydrogen to convert. With our sun, it is approximately 10 million years, so we are halfway of this period. The passive stage. The balance of gas pressure and the gravity in the active stage will be disturbed because of the sun will run out of fuel and the pressure will decrease. So it is expected to swell to a red giant in 4 to 5 million years. As a red giant, the sun will grow so large that it will engulf Mercury, Venus, and probably Earth as well. So it will bring about the destruction of life on Earth. Then its outer layers become a planetary nebula and its core will collapse into a white dwarf. The white dwarf is a really compact celestial body because it will contain more or less the 60% of the solar mass, but its size will be only Earth-sized. On the picture, you can see a comparison between the white dwarf, Pegasi b, it is in the middle, and our sun, it is in the right position. And finally, because no more energy is produced, slowly all the remaining energy is radiated and the celestial body cools down and the sun becomes a black dwarf. On this slide, you can see the whole stellar life cycle. On the beginning, you can see the huge molecular clouds. And after a big influence, there are forming some stars, the low mass stars like our sun, and the massive stars. They are much bigger than our sun. From the massive star, when it's getting old and running out of fuel, it's getting a red supergiant. And after the explosion of the red supergiant, it will become a supernova, and from the supernova, it will become either a black hole or a neutron star. The low mass star, it's actually a relative low mass. It's also huge, but comparing the massive star, it's quite small one. It's also the end of this active stage. It's running out of fuel and it's getting a red giant. And as I mentioned before, two parts of the ex-sun, it's getting apart. The outer layers is getting a planetary nebula, and the core is collapsing to a white dwarf. It's cooling down and became a black dwarf. I found a really useful and funny video on the YouTube about the stellar evolution. It's actually a 4 minutes video which shows you the complete stellar evolution. It's a bit funny way. I recommend to watch it. You can see the address above the video. So we finished this part of this video as well. So let's test your memories. Now I want you to set up an order in the stellar life cycle. Let's see. The first is the molecular cloud. And after or in the molecular cloud, is getting a protostar. Then we are getting to the active stage of our sun. It is the stable sun. Then when it's running out of fuel, it's getting a red giant. You can see the comparison in between the sizes of the original and the red giant sun. Then is getting a white dwarf, and after cooling down, it will be a black dwarf. We completed the first chapter of our solar energy course. I hope you get some useful and interesting information about our star. In the next video, we will talk about the nature of the radiation and about the factors determining the radiation arriving on the Earth. Thanks for watching. See you next time. Bye.